Bamler sur son meilleur. C'est pas mon meilleur. Ah, mais c'est vrai que c'est ce qu'il me disait, c'est assez perturbant parce qu'on voit personne dans la salle et on parle à son propre écran, mais c'est une situation un peu étrange. Ouais, mais l'enregistrement, c'est bon.
Hi, Richard. Now you're the host.
On l'entend pas. Microphone.
Your microphone is shut.
Oh, hi, how are you?
Okay, fine. You are the host and you can share your screen.
Oh, great, thanks.
The Italians went to see the football match. So, but we remain here, even in French Spain.
Ça sert à rien qu'il parle, il voit pas. Il voit pas. Si, il entend.
Yeah, but he can hear me. No?
Mais ils s'en foutent, il m'a dit qu'ils s'en foutaient de toi. Sorry, we have internal joke here because.
Oh, okay, no problem.
He's mean.
Because we are a bit tired, so.
Oh yeah.
All jokes, but we are looking forward to your lecture anyway. And I recognize the picture from yesterday. Okay.
Oh, okay.
Let's wait for a while.
What is it?
Excuse me?
Sorry, what did you say?
Oh, let's wait a little bit. And,
Oh, of course, yeah.
I'll tell you when we can start.
Sure, yeah, I'm a bit earlier. By the way, I had trouble attending Antoine's talk just before.
Yeah, and so it will be. So the talks are put online. Probably this one will be there tomorrow because it's late now, and the guy who does that has left. So tomorrow morning, probably you will be able to attend it.
Oh, I see. Oh, Antoine's talk is not a Zoom talk; it's like an in-person talk, or
no, it's a Zoom talk. You were not able to connect. Is that what you say? Or?
Yeah, I connected to Zoom, and then I was the only person on the talk.
Very strange because I was connected and I
didn't.
Maybe you took the wrong. No, I don't get. It's not possible. Do you
maybe
know?
I clicked on the wrong link. Yeah, maybe I was.
So well, if this happened another time, just send me a message and we.
Oh, okay. Okay, it's not a big deal. I was just curious to see him.
Well, you can follow the lecture in the replay anyway. So.
Oh, okay, thanks. Yeah. Yeah, it's no problem at all.
Voilà. C'est bizarre parce que moi j'ai pas eu de problème. C'est pour ça que je me connecte. On va essayer. So let me try to connect to your lecture, just to check.
Oui, il y a pas de musique. Ils sont deux lecteurs joueurs. Je sais pas, mais là ce soir elles sont très énormes. Vous aviez fermé à cause des moustiques?
Non, si jamais les gens sortaient, il y a les affaires et tout.
Ah oui.
Okay, no, I can. I was able to connect directly on the link. So, well, who knows?
Okay. Yeah, I could connect, but then there was nobody in there somehow.
Yeah,
maybe I connected to the previous version of the talk. Yeah. Maybe this was already over.
Maybe.
Oh, okay, I see. Yeah.
Okay, let's see. Okay, thanks for the link. And
oh yes.
Well, I think we are ready. It's on time, so we are ready to and happy to listen to you, Richard.
Okay, great. Yeah, thanks for coming back. Again, I've put the new handouts on the chat. I've updated them a little bit. Okay, so let me just pick up where I left off last time. Move on to the right slide here. Okay, so this class will be about trying to give you some idea how this proof of this uniqueness theorem works. Okay, so what we want to prove is the following. So we're given two singular Ricci flows, and we're assume that they are of this very nice form that we start from some cusp-like singularity at time 0, and then the singularity gets immediately resolved, and we know that we have a good characterization of the local geometry everywhere. So everywhere it looks either like a neck or like a Bryan soliton. And okay, so we have these two singular Ricci flows, and we assume that they have isometric initial data, and then we want to show that they're isometric everywhere. Okay? And so our goal will be to somehow deduce some kind of, find some kind of comparison domain N, and find a map from N into M prime, which is 1 plus eta by Lipschitz, where eta is small. And then we want to let eta go to 0 and N go to M. All right, and so then last time I briefly mentioned how this comparison domain is constructed. So you may recall the picture, and maybe this lemma now makes more sense. So this comparison domain should consist of, should be a union of some kind of product domains of this form, where the TJs are R comp squared away from one another. So R comp is our comparison scale. And we wanted the we wanted these domains to be bounded by central two spheres of strong delta n next. The delta n is a constant that we're going to choose later at scale R comp. We wanted the comparison domain to be chosen in such a way that rho is bigger than 1/2 R comp on the comparison domain, at least up until this time step J naught. Okay, so we wanted to have some lower bound on rho. So making sure that the comparison domain is not too singular. And then after that time step J naught, the comparison domain is just all of them. Yeah. And so the way this looked like was as follows. Sorry. So here we have a singular Ricci flow again, and the comparison domain would be constructed by following this staircase pattern here. Okay. So sorry, again, I should say Tj naught is the time, the first time that the scale on the tip is bigger than lambda times R comp. And please don't, forget about the 10 here. Okay, and then after this time, we just put in everything. Okay, okay, so yeah, so again, in the picture here, each n1, n2, and n3 is this product domain. We're just taking the union, and every time we have to step back a little bit. And somehow the spheres, so this region here should be a delta n neck, a strong delta n neck, so it should be delta n close to a round shrinking cylinder. And it should be at the scale that's chosen so that somehow the size of the sphere is roughly R comp, and the size of this sphere is roughly 2 times R comp. Okay, okay, and so let me just argue, okay, so this is what I just said. Let me just argue how we can construct such a comparison domain, just using some hand waving here. So first, let us recall that we assume that our flow is somehow good enough that, you know, being below scale 1 already means that we're kind of relatively singular in such a way that that we know what the local geometry looks approximately. So we're either, if the singularity scale is less than 1, then, sorry, the curvature scale is less than 1, then we're either the center of a strong epsilon neck or we're locally epsilon modeled on a Bryan soliton. Okay? And so what we could do is we could just choose epsilon being less or equal to delta n. So then all these points here are either centers of strong delta n necks, or they are or the region looks very close to a Bryan soliton. So in other words, as long as we're far enough away from the tip here, then every point here is the center of a delta n neck. Okay. Yeah. And so now the trick is just to say, well, why don't we choose lambda much very, very small? Okay? So that would be some of the quotient of the scale here and the scale here should be very, very small. And so then we can ensure that whenever we are at scale R comp, that we are not close to a Bryan soliton, and instead we have to be close to a strong delta n neck. Okay? Okay, so this way we can guarantee that in this red region, you know, that near the boundary of this red region, we're close to a delta n neck. You know, and then we just you know, then we just construct these n1, n2, and these nj's by induction. So we start at time 0, we walk somehow to the left, maybe we walk up one time step, and we go until we find a two-sphere of size approximately r comp. And we know, since the scale of the tip has to be lambda times r comp, that this point cannot be locally epsilon modeled on a Bryan soliton, and instead has to be the center of a strong delta n neck. Right? So then we know that the region here looks roughly like this, that this is a sphere of scale r comp, and this is a sphere of scale 2r comp. Okay? Then once we've constructed this time slab, what we can do is we can go forward in time a bit. We see some point that has a scale much smaller than r comp. So that means if we go further to the left, at some point we find a point again where the scale is r comp, and then we repeat the procedure. Okay? So we continue, and this procedure breaks down exactly at a point where the scale here is not very small anymore. Okay, so essentially it breaks down if somehow the size of this cap here is small enough so that this region here looks slightly like a Bryan soliton. Okay, so it doesn't look good enough like a strong epsilon or a strong delta n neck anymore. Okay, so meaning the scale here has reached somehow this threshold lambda times r comp. Okay, and so that's why we can't continue our process anymore, and instead we're just going to fill in this cap, and we're just going to fill in the whole manifold in red. All right. So yeah. Are there? So yeah, maybe I should ask: are there any questions on the construction? Okay, so maybe here's just before we proceed. Here's just one thought experiment. I could say, well, you know, this construction depends on the scale r comp. So I could make the scale r comp smaller. Okay, so what happens if I make the scale r comp smaller? Well, then the size of the time steps becomes smaller. So in particular, the capital J has to get larger if Tj has to be some fixed time. Okay? So we have to perform more of these steps. But also the scale lambda times r comp is smaller. So this threshold has to be smaller, above which we finish with the staircase pattern and just fill in the entire manifold. Okay? And so, so it turns out that this scale doesn't get it turns, or, sorry, what I should say, that also means that the time Tj naught gets smaller. So the first time that we're above this smaller scale is of course then of course smaller if we decrease our comp. Okay, and so in summary, if we decrease our comp, then Tj naught gets smaller, and also the distance between the all the Tj's is smaller. And so we could ask, well, what happens to J naught? And you know, it's not hard to see if you do some back of the envelope computation, that as you make r comp smaller, J naught has to go to infinity. Okay, so this is kind of the problem. We can't somehow, our lives doesn't get easier if we make r comp smaller, because then we will have to perform more and more of these steps. Okay, so we really have to come up later with some kind of procedure that's independent of the number of steps that we perform. All right, so okay, are there any questions so far? Okay. All right, so okay, so this is the comparison domain N, and I'll denote this by comparison domain N, or sometimes I'll denote it by, you know, the corresponding time slab by Nj. Okay? So what we need to decide next is how do we construct the corresponding comparison map, okay? So again, this is now just should symbolize the comparison domain. I guess at some point we have to fill it in. And what we need to do now is we need to decide how to construct a map phi from N into M prime, such that the inverse of this map evolves by harmonic map heat flow, and such that this map is 1 plus eta by Lipschitz, so meaning that this corresponding perturbation is small. Okay, and so here is roughly the strategy that that we want to follow. Well, first of all, the map at time 0 is going to be given. Okay? So if this was the time 0 slice, then this map is just given by the isometry. Okay? then in our first step, we will have to extend the map from time 0, from this n0, up until time t1. But now our comparison domain has a boundary. Okay? So we will now need to solve the harmonic map heat flow with, or for any time step with this initial data. And we have to solve it for the inverse of the map, okay? So we have to find some kind of map from this domain into M prime, such that the inverse of this map, at least locally, we hope that it's locally defined, solves the harmonic map heat flow equation. Okay? But now we basically have, essentially what this means is we need to solve the harmonic map heat flow equation with a boundary term here, okay? because our domains have a boundary. And it gets even a bit more awkward because, the boundary here looks very nice and rectangular, while we actually have to solve the harmonic map heat flow equation for the inverse of phi. Okay? So this gets a little awkward. And so I think there are many ways of solving this harmonic map heat flow equation, many analytical ways. I'm sure you can just solve the harmonic map heat flow with a boundary term, but then you have to worry about some awful boundary behavior. And so the easiest way that we found to somehow get around this boundary issue is by what we call grafting on half cylinders onto the boundary and its image. Okay, so the idea that we followed was to say, well, this region here looks very close to a round shrinking cylinder. So why not just cut off the right part, the right-hand side of this picture, and glue a precise shrinking cylinder using some cutoff function. Okay, so then in doing this, we've constructed some non-singular flow which almost satisfies the Ricci flow equation. Okay, so it satisfies the Ricci flow equation here and somewhere further away from here. But in the gluing region, it only satisfies the Ricci flow equation up to some error. And then we do the same in the image. Again, in the image looks relatively cylindrical near this boundary, and we're going to graft on another half cylinder. Okay? And then once we have these two flows, which are now concern complete families of complete metrics, we can solve the harmonic map heat flow equation between these two families of metrics. And then later we just remove these half cylinders and we restrict to some smaller domain. Okay? So in doing so, we obtain some solution to the harmonic map heat flow equation, which hopefully is regular enough near the boundary. Okay? So it doesn't satisfy any boundary conditions, but hopefully it should somehow behave the way we would expect it to behave in a cylinder. All right, so maybe this is just the technicalities, but what we can essentially do is, given phi at time tj, we can extend phi to this time slab nj plus 1 and solve the harmonic map heat flow equation. Okay, so recall, this is similar to what we've done in the non-singular case. Okay, in the non-singular case, we started with some phi, which was an isometry. So h was 0 at time 0. And then we solved the harmonic map heat flow equation forward. And then this implied that h has to be equal to 0 everywhere, and that we have an isometry. Now, the added difficulty here is that we may have error terms coming in from the boundary. So we did some weird constructions on the boundary, and these boundaries, they may not match up very well. Okay? So now if we want to control h somewhere in the interior of nj plus 1, it's not only important what h is at time 0, it's also somewhat important what h is near the boundary. And so basically what we need to analyze is how these two, how the geometries near the boundaries fit together. And so essentially what we get is the following result here. We get that if somehow the precision of the necks here near the boundary, so that's called delta n. So this the precision of the strong. So we know that this region here, the flow in this region looks cylindrical to degree delta n. If this is smaller than some constant, depending on, let's say, some constant eta prime, and if h is bounded by some other constant, which is maybe much smaller than eta prime, somehow near this boundary at time tj, so maybe in this region. Okay, so if H is very small in this region, and if we know that both flows are sufficiently cylindrical in this region, then H is smaller than eta prime near the boundary, somewhere near the boundary. I'm being a little imprecise for all positive, for all times past time tj. Okay? And so the idea to prove this is via some kind of limit argument. Basically what I'm saying is, I'm just saying, giving us a relaxed version of saying that if we start from something that's exactly a cylinder and H is exactly equal to 0, then it remains 0. Okay? So now I'm saying if we start from if we look at some region that's very close to a cylinder, and we start from some initial condition that on a very large subset, where H on a very large subset is very, very small, then H will remain relatively small in a neighborhood, in a parabolic neighborhood of this boundary, this parabolic boundary. All right, so this can be obtained by some limit argument. Okay? Okay, so again, in other words, somehow the influence, so the boundary will influence somehow the precision of phi, of this almost isometry phi measured by H. And this precision is influenced by delta n and somehow how small H was near the boundary here. And it somehow always gets a bit worse. Okay, sorry, maybe I should ask, are there questions so far? Okay, so what do we need to ensure to carry out this extension step? Right? And recall, we have to construct phi inductively for every j. So we have to continue the step, and we have to end up with the same estimates later that we've started with. Yeah. So what do we need to ensure? Well, first of all, we need to ensure that H is very, very small near the boundary of nj plus 1 at time tj for some small eta prime. That's again smaller than eta. And then we also need to make sure that H is smaller, then eventually we want to make sure that H is smaller than eta everywhere on nj plus 1. Okay? So this is basically the important fact. But in order to achieve smallness, we have to somehow we also have we also have to have much better smallness in this region. Okay, so how can we maintain these bounds? And so the idea is to use the semi-local maximum principle that I showed you in the previous class. Right? So how do we do this? Well, first let me fix a constant e, and e should be an exponent, and e should be approximately 100. And you'll see later why I have to choose this so large. And let me consider this quantity q here, which we essentially gives us a way of measuring h and a way of applying the semi-local maximum principle. And now I'm going to choose a threshold for q bar. Okay? And the threshold for q bar should be approximately this number. So what does this mean? Why did I choose exactly this number? Well, this number has the following properties. It shows us that whenever we are on nj plus 1 at any point, then this bound here will imply that H is bounded from above by eta. Right? Recall that the scalar curvature is roughly bounded from above by r comp to the -2 on nj plus 1. Okay, so then if you do the computation, you get that this bound implies this one. Okay? So that's something that we always want. We want to be able to use this bound to control H in the way we want it to. On the other hand, we also get some version of the kind of the reverse implication. Right? So we get that if H is smaller than some number eta prime, which I choose sufficiently smaller than eta, just depending on these other factors, then near the boundary of nj plus 1, this would imply that q is bounded from above by q bar. Okay? So recall, near the boundary of nj plus 1, the scalar curvature is bounded from above and below by something that's comparable to r comp to the -2. Okay? So near the boundary of nj plus 1, we can also go in the other direction as long as we choose this constant smaller. All right. And so now this bound Q is bounded from above by Q bar. Can it be maintained or propagated forward using the semi-local maximum principle? Okay? So I've showed you this example using the semi-local maximum principle, where we maintained a bound just in a more classical setting. And again, this can now be done in this setting. Okay, so somehow the idea would be to say, well, what happens at a point where Q is maximal? Well, if you go to a point where Q is maximal, then just by the semi-local maximum principle, Q has to be bigger somewhere in a parabolic neighborhood around this point. Okay. And so here's some small difficulty, which occurs when we're close to the boundary. So if you're close to the boundary, there may not be the corresponding parabolic neighborhood given by the semi-local maximum principle may not fit into this nj plus 1. Okay? And so that's why near the boundary, we need to already know that Q is bounded by Q bar. Okay? So that's why I want that this is true not only on the boundary, but somehow near the boundary. And by near, I just mean near, in a distance in such a way that if you're not near the boundary, then we can fit in these parabolic neighborhoods into nj plus 1. Okay? So, all right, so this is how we can ensure property 2. Okay? So if we can perform this step and if we have control of h near the boundary to this degree eta prime, then we can propagate the bound on h forward in time, and we can continue doing this without ever losing anything that depends on j. Okay? So the other question is, how can we ensure that exactly near the boundary of nj plus 1 at time 0, so maybe that we should have done this before, how can we ensure that we have an even better bound on h, right? So near the boundary of nj plus 1 at time tj, we need a much better bound on h than we have given from these bounds. Okay, and so here is where we use the, I'll get back to this question in a moment. Here's where we use this, where we use again the semi-local maximum principle, and we use the fact that this constant alpha in the semi-local maximum principle can be chosen as small as we want if we just choose the size of this parabolic neighborhood large enough. Okay? So let me go just backwards to show you the semi-local maximum principle. Maybe I should have added a slide here. So the semi-local maximum principle said that Q at the base point is bounded from above by some alpha times the supremum of Q over the parabolic neighborhood, and alpha could be chosen very small. And if we just choose alpha small, then that may just mean that we have to choose L very large. So if you choose the parabolic neighborhood very large, then we can make alpha very small, so we can get an arbitrarily good improvement. Okay, okay, so let me just go back to this other slide. Okay. Okay. So essentially what we can do at points near the sphere is we can take some extremely large parabolic neighborhood around these points in such a way that alpha is exactly equal to eta naught divided by eta, and then we get the desired improvement. Okay? And so this is only possible if this huge parabolic neighborhood fits under the staircase pattern. Okay, so the boundary of the previous nj, okay, so I didn't draw the boundary here, has to be very, very far away from this sphere of size 2. Okay? Okay? So in other words, if the staircase pattern is in some sense flat enough, then we have this extra improvement here. Okay. So this is how we can get the number 1. Okay. So sorry, there was a question. How do we choose H and T? Okay, so that's maybe I should address this. I wanted to omit this issue a little bit. So capital T for me is just some time. I could just set it equal to 1. Okay, this is somehow the time of existence of the flow. And capital T is chosen in such a way that at capital T, that's the last time where we perform any of these operations. Okay? Capital H is chosen by this, is chosen in the statement of the semi-local maximum principle. So we have to choose H large enough so that the semi-local maximum principle can be applied. Okay? So H, I think, depends on E via the semi-local maximum principle. So once we fix E, I think we can fix H. Okay. Yeah, so I wouldn't worry too much about the exponential factor here, but you know, somehow it's a little annoying. That's why we have to sometimes put an e to the minus ht, because this could be some of the smallest that this factor could be. All right. Okay. Yeah. Oh, thanks. I hope that answers the question. All right. So let me just recap. So we have these somehow. We use the semi-local maximum principle in 2 ways. So first of all, in order to just maintain a bound, the desired bound that we just need everywhere on the comparison domain, we just use the standard semi-local maximum principle, where alpha is maybe, let's say, 1/2. All we want to say is that the bound Q is bounded by Q bar is maintained forward in time, right? So that if that's true somewhere, then it's just going to be true later. For number 2, we use somehow the fact that we can choose alpha as small as we like in the semi-local maximum principle, and then we get some additional decay that we can use here. And we want H to be very small here, because this will guarantee that in this solution of the harmonic map heat flow equation, that H is small near the boundary. Okay? And so there's some kind of bad dependence that we have to overcome. Okay? And so in order to get this additional decay, we have to make sure that the staircase pattern is very flat, so that the steps are very far away from one another. So in other words, that the distance of this 2-sphere to the of the 2-sphere of size 2 times r-com to the sphere of size r-com somewhere very far to the right is very large. Okay. Are there any other questions? Okay, so I'm sorry, there's a lot of hand waving and technical details that I have to skip here. So this, I hope it's not too confusing. I hope you get the gist of the argument. Okay, so let me recap. Maybe we could just recap this construction by understanding how we have to choose all these constants, lambda, delta n, epsilon, and so on. Yeah, so let's just go over the construction again. Yeah. So first of all, we needed to ensure that when we constructed the comparison domain, we needed to ensure that the boundary of the comparison domain consisted of regions that looked like delta n-nix. Okay? And I said in order to achieve this, well, we have to choose epsilon less than delta n to make sure that locally every point looks like a delta n-nic or is close enough to a Bryan soliton. And we also had to choose lambda small enough, depending on delta n, just to ensure that we're not too close to a Bryan soliton. We always wanted to be in the case where we're close to a delta n. Okay, so the important thing is we had to choose lambda small enough, depending on delta n. Then when we solved the harmonic map heat flow equation, we wanted that H is less than some eta prime. And recall eta prime is just this number here. It's basically some constant times eta. And in order near the boundary of the partial parabolic, near the boundary of the comparison domain. And so in order to achieve this, we had to make sure that somehow these regions look sufficiently neck-like, and that we're starting with some H that is even bounded by eta naught. And both of these guys had to be chosen small depending on eta prime. Then next we had to apply the semi-local maximum principle to maintain this bound. And well, in order to do this, eta had to be small enough, and eta prime had to be equal to this number. And then lastly, we had to have this extra interior decay estimate in order to show that H is less than some constant eta naught, which is even smaller than eta prime. And we could only obtain this by choosing the boundaries of the comparison to make sure, in order to achieve this, we had to somehow make this staircase pattern extremely flat. Okay, the steps had to be very far away from one another. And the only way to guarantee this bound is to say, well, near every time that we see a step, we have to have a very, very good delta n. Right? So we had to just make, as long as we make delta n very, very small, then well, we know it takes a long time to if we see a sphere of size 2 times r comp and a sphere of size r comp, then there has to be a very large distance between them. Okay, so remember, this has the scale here is 2 times r comp, while the scale here is r comp. Right? So if this is somewhere in the middle of a delta n, then this distance has to be very large depending on delta n. Right? So we have to make delta n less or equal to delta some constant that's depending on eta naught divided by eta. All right, so let's summarize what is some of the dependence. So eta will influence eta prime will influence eta naught via this quotient will influence delta n, and then delta n will influence epsilon and lambda. Okay, so we can first choose eta, then we can choose eta prime, then we can choose eta naught, then delta n, and then epsilon and lambda. Okay. So in the real proof, I think there are like 15 such constants, and there are much bigger diagrams that show the dependence of the constants. Right? But it's somehow possible to choose these constants in a way. Maybe I'll leave this up for a moment. Any questions? Okay, so what I've done now is I've described how we can construct a comparison domain and how we can construct the comparison map on some of the first part of the comparison domain. Okay? So I've tried to I hope I've somehow conveyed the idea how to construct the comparison domain comparison map on that shaded domain, a root domain. Okay. So the next step will be now to extend the construct a comparison map on this domain. Okay. And so the first step will be to extend the comparison map over onto this cap. Okay. So this comparison map phi is only defined on that ruled area, and so now we have to extend it over this cap. Okay. And so just to recall again, we know that Q is bounded by Q bar here, and this will roughly translate into a bound of this form, right? That H is bounded from above by R to the E. Right? Okay? And so the constants are chosen in such a way that Q bounded by Q bar essentially implies that H is bounded by eta here, but towards the left where R gets smaller, this bound actually improves. All right, so we need to somehow address this question. How can we extend a map that's defined everywhere except on some kind of 3-disk? How can we extend it over the entire disk? And so this is what I refer to as the cap extension problem. Okay, so here I've just magnified this area. So I'm going to magnify this area. And so this is some of the final time slice of the some of the final comparison domain or the J0 step. And the comparison map here is defined on this red domain. Okay? And this domain looks very close to a Bryan solid. You know, the entire region looks very close to a Bryan soliton at scale lambda times r comp. So I should have added lambda times r comp here. I'm sorry. Okay, so what's the diameter of this ball? So it's not hard to, it takes a while to compute that, by the fact what the Bryan soliton looks like asymptotically. But essentially the diameter of B is lambda to the inverse times r comp, okay? And so the important thing here is that if I make lambda very small, so if I make the scale here much smaller than the scale here, then the diameter of B gets much, much bigger, okay? So the smaller I make lambda, the more cylindrical this region looks like, and somehow the longer B becomes. And phi is defined on this red region, and it's somehow it's a bi-Lipschitz map, and, or, you know, so at least a bi-Lipschitz map onto its image, 1 plus eta bi-Lipschitz map. And by what I've explained last in a few slides ago, we even have a slightly better precision of phi near the boundary. So we know that phi is essentially 1 plus eta naught by Lipschitz, where eta is more or less related to, eta naught is more or less related to eta. Okay, so we know that we have some map whose differential is very close to 1 onto some other region, which also looks like a Bryan soliton. Okay. So, and so this, now we have this kind of problem. We have an almost isometry given from a region, from some annular region of the Bryan soliton to some other annular region of another copy of the Bryan soliton, and we need to extend it to become some other almost isometry over the entire Bryan soliton. Okay? And so this is a very unstable problem, or, you know, somehow a very sensitive problem, because the problem is that if you make this, if this ball gets very long, then you need to have extremely good precision here in order to extend the almost isometry over the to the entire Bryan soliton. Okay, so you can recall that here the region looks almost cylindrical. So maybe you've chosen some really good almost isometry, which just unfortunately is just a little, it's just shifting the radial parameter a bit to the right or to the left. Right? Okay. So you will hardly detect this from the fact that you have an almost isometry, because somehow shifting to the right or to the left will hardly increase the diameter of the cross-sectional two spheres. But like, in order to extend, in order to somehow solve the extension problem, this causes a much bigger problem, because you're really shifting, you're shifting by some kind of macroscopic amount. Okay? Okay? And so I kind of like this, to compare this problem with some kind of, like kind of, I call it some kind of cantilever. So what the problem that you essentially have is that you want to somehow match, two different pens with one another, and you essentially know that these pens may be very long, and you're essentially just holding them with a little bit of wiggle room on one side. Okay, and well, now if somehow the pens are very short, then they might match up pretty well. But if the pens are very long, then even if you just only have a little bit of wiggle room here, they might just diverge a lot from one another. So if they're very long, you really have to hold them very, very precisely in this place, so that some of the difference doesn't show up later. So this is what this is some kind of cantilever problem. Okay? Okay. So just to state this in mathematical terms, what I mean by this is that, well, if we need to so in order to extend over something that is roughly size lambda inverse, we will just have to choose the precision of the almost isometry that we're starting with very, very good. Okay, so if we want to obtain a precision of lambda later, and the diameter of B is given by lambda inverse, then eta naught, so the precision that we're starting with, has to be very, very small, depending on these two parameters. Okay. But here's the problem. Well, we've already chosen lambda depending on eta naught divided by eta. Okay. Okay, so we can choose eta naught depending on lambda. Okay, so this would give us a circular dependence of the constants. So this somewhat, the naive strategy here wouldn't work out. Okay. And so here we need so here we really need a new idea. And so the idea is now the following, and it's somewhat unintuitive. So the observation is that, well, near this boundary here, or I should say maybe on the entire comparison domain, we have this bound Q is bounded by Q bar. Okay, we always use this bound to just control H and say essentially that H is bounded by eta. Okay, because we could, this bound implied that H is bounded by eta. But this bound gives us a much better estimate. It gives us that H is bounded by eta times something that's essentially equal to 1 near the boundary of the comparison domain, and then goes to 0 as we move away from the boundary domain. Okay, it becomes arbitrarily small because the scalar curvature will become much, much smaller than r comp to the -2 as we move away from the boundary. Okay? So in other words, the precision of this comparison map really increases significantly if we move away from the boundary of the comparison domain. Okay? So if you're going even further away from the cap, then the precision of this almost isometry gets much better. Okay? Of course, somehow, if we have, and so now the idea is to, instead of extending this map over B, the idea will be to first remove a large part of this comparison domain. And then we have the problem of extending some map over an even bigger domain. But now we have much better almost isometry properties near the boundary. Okay? Okay. So we have these somehow two competing issues. First of all, the length of the cantilever, or the length of the domain over which we want to extend our almost isometry, and the precision of the almost isometry that we're starting with. Okay? So if you first remove some domain here, if you restrict our map to some smaller domain, then the first problem gets harder. We have to extend a map over a larger domain, so that's a harder problem. But the second aspect somehow it works in our favor. Somehow the almost isometry gets better. Okay? And so the idea will now be to show that the second effect dominates the first one. Okay? And so, I always like to somewhat imagine this as some kind of, as I said, as some kind of cantilever. So let me just show you these two pictures that I was kind of thinking of when we came up with this solution. Here's a picture. Here are two pictures of cantilevers. Okay, so cantilevers are just things that are somehow protruding that you have to hold on one end, and that are hard to engineer because they're very long. Okay, yeah, and so I just drew these two pictures of cantilevers. One is a long cantilever and one is a short cantilever. Yeah? And so you could ask, where do you feel safer? Well, as I said, this is a long cantilever, and you should probably feel unsafer standing here on the ledge of a long cantilever because you think a long cantilever might vibrate more and things like that. But what is also important is how good the engineering here is. And this seems kind of a very solid construction here. So I would feel much more comfortable standing here than on a short cantilever where somehow the attachment doesn't seem to be very, very rigid. Okay? So this is exactly this idea. Some of the engineering has to overcome the length of the cantilever. All right, so let me put this into mathematical terms. So again, here's our problem. We have an almost isometry given on this part, and just so that I can somehow make our formulas more precise, let me simplify the setting a little bit. Okay, so let me first rescale the situation and normalize the curvature here at the tip to be 1. Okay, so I really want this region to look like a Bryan soliton. Let's just say for simplicity, the flow at some time slice is isometric to a Bryan soliton, just to simplify our discussion. Okay? So this is a Bryan soliton, and then very far away on this Bryan soliton, we're given an almost isometry into another copy of the Bryan soliton. Let's just say for simplicity, it's at the same scale. And what we know is and what we want to do is we want to extend this map over onto the blue part. Okay? And then the bound that we have is that h, essentially is that h divided by re is bounded from above by some q bar. I think I have to adjust this after rescaling. Okay. So but the important thing that I just want to mention is that h, as I move away here to the left, the scalar curvature goes to 0, and so this bound will imply that h decays polynomially approximately at the rate e. Okay. And so now here's the idea. that this is somehow the main theorem. It says that if we just choose E large enough, and recall we can choose E as large as we can, then this polynomial decay of H, is very, very fast. And this dominates the complications that arise from extending a comparison, extending an almost isometry over a larger domain. Okay? So in other words, what I'll do here is now I'm going to choose some D, as a beta is some constant, which should govern the precision of the outcome, the map, which should be the outcome. And I want to choose D very, very large, right, depending on beta. So D should be this length. And in reality, D should be much, much longer, but I didn't have space on the slide. And then I'm going to mark this disk here, okay? So this is just some 3 disk. Okay? So this should be a 2-sphere boundary here. And then what I'm going to do is I'm going to restrict phi to the comparison domain minus a ball of radius d around the center here. Okay? So I'm essentially just removing this part from the domain of phi. And then I claim that given this phi, I can now perform an extension of to some map phi hat that satisfies this improved this bound. Okay? So this almost isometry property. Okay? So in other words, so again, if somehow E is chosen large enough, then somehow choosing D larger works in our favor. Okay? If E is somehow chosen too small, then choosing D larger is probably a bad decision on our side. Okay? And I can even improve this, I could maybe even improve this bound to beta times r squared. I can maybe make this bound better as r goes to 0. Yeah. So, E is 100, so it should be working out. Okay, are there any questions on this? Okay, so let me just show you the picture again. We have a map defined on this ruled region, and we wanted to extend this map over onto this cap. Right? But instead of doing this, what we're actually going to be doing is we're going to restrict the given map to some region maybe up until here, okay? So that it's actually not defined in an even bigger disk. And then this improved precision that we have here will allow us to extend over the disk with a better precision. All right, so let me now just conclude the proof of the theorem, or at least sketch what some of the ideas are. Okay? So as I said, we can extend the map, I should say, restrict it to some smaller neighborhood onto the entire manifold. So this is just the entire manifold via this Bryant extension principle at time tj naught. Okay, so what do we get when we do this? Well, first of all, Q is going to remain bounded by Q bar on the complement of the extension disk, because we haven't done anything to phi on this extension disk. And on the extension disk, we have some bound of this form where H is bounded by beta. Beta just gets small enough as long as we make this extension disk large enough. Okay? And I'm going to choose these constants in such a way. I have a lambda times r conv. This just comes from rescaling. Okay. Okay, so this is essentially the scalar curvature modular rescaling. Okay, so in the previous slide, or 2 slides before, I assumed that the Bryant soliton was at scale 1, and now the Bryant soliton is at scale lambda times r conv. So what do these 2 bounds imply? So they imply that on the entire manifold, first of all, well, Q is going to be bounded by some large constant times Q bar. Okay, so we have a good bound on the complement of the extension disk. And well, we have this bad bound on the extension disk. So we will, in order to have a bound of this form, we have to add in a very large constant here, depending on lambda. Okay, so that's one type of bound. And the other bound will imply that somehow, well, on the extension disk, we can essentially rewrite this bound as a bound on some quantity which I'll call Q star. And Q star is essentially defined in the same way, only that the exponent now is 2 instead of E. Okay. So this bound, I just divide by r squared, so I get a good bound of this form on the extension disk. And this bound is much stronger than a bound with a smaller exponent. So this bound here will imply a bound of this form. Okay? So as long as I'm somehow above scalar comp, the bound on Q will imply the bound on Q star. So I have this Q star bound. And now I can use the Q star bound, and again, the semi-local maximum principle to somehow control the flow or control H forward in time past that Bryant extension, past the extension. Okay. So this can be maintained using the semi-local maximum principle using the exponent 2, and this somehow the threshold here is chosen in such a way that it implies that H is bounded by eta everywhere. Okay. And so then I'm basically done. This now I've done my Bryant extension, so the rest of the flow is just a standard Ricci flow, and I can maintain this bound forward in time for as long as up until time capital T, up until where the flow exists. Yeah. Here's just some other remark. Let's assume we don't only have a single cusp in the beginning. Let's say we have more than one cusp, or somehow the manifold will become a cusp again, or something like this. Then it's often useful to. So what we need to do in this case is we can't really forget about a bound of this form. Right? So we somehow need to maintain the Q bound because we might need it to perform another cap extension. Okay, so in other words, if I have to perform more than one cap extensions, I cannot forget the Q bound after the first cap extension. Okay? So I have to use this bound here. And now, again, I use the semi-local maximum principle, in particular the interior decay part of this, to show that after waiting for a sufficiently long time, this bad bound eventually improves to the good bound. Okay, so as long as I somehow don't perform any construction close enough to the cap extension, I'm going to get back my original bound. Okay? And so this is some of the proof of the theorem. Okay, so are there any questions so far? Okay, so let me spend one more slide on, so this is some of the proof in the toy case where we have this very nice behavior. A single singularity resolves and doesn't run into another singularity and so on. And we know exactly what some of the local models look like. But somehow if we look at general singular Ricci flows and we want to establish uniqueness, then there are a few more problems that arise. And so I'll just show you one slide and hand wave what some of the ideas are that go into the general proof. Okay. So first of all, recall that we somehow assumed that the scale at the tip increases or weakly, okay? And so this allowed us to deduce that the tip always looked like a Bryant soliton. Okay? So a priori we didn't know this fact in our proof that these tips always look like Bryant solitons. I mean, this is now true because we have a classification of kappa solutions, but this was just done recently. Okay, so in order to get around this, our strategy was to somehow be very careful to decide when to perform a cap extension. So we had to really do it at the right time. We had to wait until both the cap in M and in M prime looked like a Bryant soliton. And it's not hard to prove that there have to be times when these when the time derivative of R is negative at these tips, and therefore the tips have to look like Bryant solitons. Okay, so there are many times, but maybe not all, where somehow it's easy to prove that the tips have to look like Bryant solitons. So we just have to we have to perform the cap extension at the right time. As I mentioned before, there may be more than one cusp that resolves, and this may result into having to perform a cap extension at 2 different times or at several different times. Okay? And so the solution here is, again, to just continue the neck and cap extension process after the first cap extension. Okay? So we really have to maintain the bounds on Q, even though we've already performed a cap extension. And then the other problem is that we may have, after we've performed a cap extension, the same tip may run back into a singularity again, and we may have to, and may become singular, may become singular again, or the curvature may just increase so that we won't be able to perform our usual estimates. And so this essentially happens when there's an accumulation of singular times. And the solution here is to perform a cap removal when the curvature exceeds a certain threshold. Okay, so if the curvature grows too large, then at some point we may have to remove a cap again. And then we may have to do another cap extension. And so in order to, and we have to somehow ensure that somehow the cap extensions and cap removals are sufficiently separated in space and in time, so that we have somehow time for this bound on Q to recover to the original bound. Okay. Again, so this somehow adds to some of the technicalities of the proof. All right, are there any questions on this? Okay, so then next, I just want to also take a step back and just review the proof that we've that I've tried to somehow sketch here, and just make the statements of the main results as precise as we can, and talk about some further byproducts that the proof has. Okay. So let's just state the main results in the best possible way, and this will help us in a moment. Okay. So first of all, what we've proved, at least in the toy case, is this uniqueness theorem. Okay, so we've proved that we have two singular Ricci flows, and we have an isometry at time 0. Then there's a unique extension of these singular Ricci flows, which is an isometry between Ricci flow spacetimes. And so this is what we proved, and this can be proven in the general case. Here's maybe just one remark here. In this proof, it's really not important that we start from some compact surface. Okay, so we could really start from some non-compact initial data, some even infinite volume, infinite diameter, or anything like this. And we could even start, or in fact, we've done this. We've started from singular initial data. Yeah. Sorry, don't worry about this. What I put in parentheses. That's incorrect. Then. Okay, so we do get a uniqueness of Ricci flows. So if we know we have two Ricci flows that are isometric in the beginning, then they are isometric. But there's a much weaker. Oh, sorry.
You say singular, so it's any type of singularity, or you ask for certain type of singularity, the one that appears along the Ricci flow.
Oh, okay, that's a good point. Okay, so I should be honest here. So it's only singularities that can be described using the canonical neighborhood assumption. So essentially, they can only be these cuspidal singularities. Okay. Yeah, so I need the flow at time 0 to satisfy the canonical neighborhood assumption. That means high curvature regions still need to look like necks or caps. Okay, so that, of course, restricts what kind of singularities we see. Yeah, thanks for the question. Yeah, I should have clarified this. All right, so in the uniqueness theorem, we can say that if we have isometric initial data, then the flows are isometric. But as you've seen in the proof actually established isometry in the very end when we let eta go to 0. Okay, so essentially what the proof actually did is it first established some closeness of two flows given isometric initial data, and if you look at the proof carefully, you'll see that you don't even need isometric initial data if you just want to establish closeness. Okay, so it's enough to have two flows with very close initial data and show that then there is an comparison map that allows us to compare, that establishes some almost isometry between both flows. Okay, so essentially, as a byproduct of this proof, we get what we call a strong stability theorem. So it allows us to say that two flows are close if the initial data is close. Okay? So that's why we call it a stability theorem. And now some of the surprising thing is that the stability theorem has relatively weak assumptions on the kind of Ricci flow spacetimes that we're working with, because in these proofs, we're really not working at small scales. We're only working above scale R comp or lambda times R comp. And we don't really we don't really care what the flow does below any, at any smaller scales. Okay? So the idea here is that we have a stability theorem for Ricci flow spacetime. So they don't even have to be zero complete. They just have to be defined up until the scale up to this. They have to be defined above the scale above which we're working. Okay. So let me now phrase this, and I'm sorry, you can skip the slide if this is too technical. So what we can prove is that there, given delta t and e, that we can find two constants epsilon can and epsilon, such that for any scale r, the following is true. So suppose that we have two Ricci flow spacetimes over an interval from 0 to t that are not, they don't need to be singular Ricci flows, they only need to be epsilon r complete and satisfy the epsilon can canonical neighborhood assumption at scales between epsilon r and 1. So this doesn't even have to be equal to 0, okay, as in the singular Ricci flow. Then the following is true. Assume you have a diffeomorphism between, at time 0, between two open subsets of the initial time slices, u and u prime, such that u contains at least the points where the curvature is not too big. And then so that this map satisfies, basically the same bound that we've been using in the proof. So I've used here the norm of the curvature, but you could also write the scalar curvature to the power of e. Okay, so we want to have a better bound at larger scales, or we allow a relaxation of the bound at smaller scales. We don't want to have too much distortion of the curvature, so that's just a technical point. We can skip over this. Then there's a time-preserving diffeomorphism between between some open subset of the spacetime to some open subset of the spacetime m prime, such that again, u hat contains the points where the curvature is not too small, not too large. Phi hat evolves by the harmonic map heat flow. And again, we have a bound as well, basically a bound that's comparable to this q bounded by q bar bound. And of course, it's equal to phi naught at time 0. Okay, so it's equal to phi at time 0. Okay, okay, so so this is some of the most general result that we get from this proof strategy. And again, I just want to highlight here that surprisingly in this proof, m and m prime, sorry, this should be m prime, only need to be defined above scale epsilon r, right? They may even, you could even say you take a Ricci flow, you take two Ricci flow spacetimes that somehow violate the Ricci flow equation below that scale. They may do something completely different below the scale, and somehow the strong stability theorem would still be true. So this is somehow, there's some kind of censorship property that the strong stability theorem gives us. Okay, so we really just need the Ricci flow equation to hold above scale epsilon r. And so here are some consequences of this. So let me run through these consequences, which I think they're kind of interesting, and they will lead us to the continuity result later. So first of all, a property of this form is going to be important if we look at Ricci flows with surgery. So Ricci flow with surgery is not a singular Ricci flow, it's only defined above scale epsilon r. Right? So this is where this comes in handy. And so the strong stability theorem, in other words, allows us to compare the corresponding Ricci flow spacetimes arising from Ricci flows with surgery. Okay? And so here's a nice result that we get from this. Right? So assume that we have a Riemannian manifold, and we consider a sequence of Ricci flows with surgery. I'll already represent them by the corresponding Ricci flow spacetimes, and I'll denote them by m delta I. Delta I should be the surgery scale. And I'm going to let delta I go to 0. Okay? So if I do this, I get these Ricci flow spacetimes that are delta I complete and satisfy the canonical neighborhood assumption above scale delta I approximately. Okay? And now I can apply the strong stability theorem to these flows and to the corresponding singular Ricci flows starting from this guy. And I obtain that I have convergence, okay, of the Ricci flows with surgery to the singular Ricci flow. Okay? Convergence in the sense that there are these comparison maps. Okay? And so this is basically similar to what Kleiner and Lott obtained when they constructed singular Ricci flows, but they obtained a compactness theorem. So they could only show that after passing to a subsequence, we have convergence of this form. And now it turns out that even without passing to a subsequence, we always have convergence to that unique singular Ricci flow. Okay, so this somehow shows that every Ricci flow with surgery is some kind of approximation of this singular Ricci flow. All right, so this is one application. The next application is more like some of the weak version of the stability theorem. So what I'm going to do now is I'm going to take the strong stability theorem, but I'm just going to apply this only for singular Ricci flows. And so this will remove a lot of the extra baggage in the argument, in the statement. So what I get here is essentially, what I get is that for every delta and t, there's an epsilon, such that the following is true. If I take two singular Ricci flows, and if I assume that there's 1 plus epsilon by Lipschitz map between the time zero slices, so let me not even worry that, let me just assume that the map is defined everywhere at time zero. Then there's a 1 plus delta by Lipschitz map between large regions of the corresponding singular Ricci flows. Okay? So you had prime, where you had contains the set of points where the curvature is not too large, and phi hat is somehow big enough, is equal to phi at time zero. Okay. So if I have nearby initial data, I get flows that are comparable on points where the curvature is not very large. At points where the curvature is large, even the structure of the singular set may be different, so there's no hope in comparing both flows. Okay, so in theory, M could be, there are examples where M is a non-singular Ricci flow, and M prime is just a perturbation of this flow which happens to have a small singularity. Okay? So there's no hope in comparing these two flows at points where the curvature is too large. Okay, sorry, normally you say for every delta there's an epsilon, but here I turned it around. And so here's another application. Let me now say this in terms of a sequential, convergence. So we get some kind of convergence statements of singular Ricci flows, and this will relate to continuous dependence in a moment. So sorry to go through all these statements. So what we get is that is the following theorem. So let's consider a sequence of singular Ricci flows, Mi, such that there is a sequence of diffeomorphisms between the initial time slices of some singular Ricci flow M infinity and the initial time slice of Mi, such that if we pull back the initial condition of Mi via phi, then we have a local smooth convergence to G infinity at time zero. Okay? So we just assume that we take a sequence of singular Ricci flows that at time zero converge in the smooth Cheeger-Gromov sense. Then the previous theorems imply that there is a sequence of time-preserving diffeomorphisms phi hat I from some subset of M infinity to some subset of Mi, such that the subsets Ui converge to M infinity, that there's some increasing sequence, and such that the pullbacks of the corresponding matrix Gi converge to G infinity on all of M infinity in the local smooth sense. Okay. And now we can even get a statement on the time vector field. So what happens to the pullbacks of the time vector fields? Well, the time vector fields, remember, the pullback of the time vector field essentially tells us how much the harmonic map heat flow moves. Okay? And the harmonic map heat flow is somewhat determined by the discrepancy between the pullback of the metric and the metric itself. Okay? So if we have this convergence, this smooth convergence, then we have smooth convergence of the time vector fields. Okay? Okay. So this is maybe some of the closest way that we've gotten to stating some kind of continuous dependence of singular Ricci flows depending on their initial data. Okay? So what I would like to do in the following, in the last part of this chapter in this talk, is to somehow state state a result that somehow shows that we have continuous dependence on initial data for singular Ricci flows. And you know, I want to state it more, not in somewhat the sequential version. I want to state it as saying, suppose we have some continuous family of metrics on a given manifold. There's some kind of continuous family of singular Ricci flows arising from this. Okay, so this is somehow the goal of making this precise. Okay, so how do we say that a family of singular Ricci flows is continuous? Okay? Recall, singular Ricci flows are only unique up to isometry. So for every parameter, every singular Ricci flow could live on a different manifold. So you know, so we need to do some work to somehow state continuous dependence more precisely here. And it turns out there are two methods. So there's one which I'll call the quick and dirty method, and I'll spend the next 2 slides on this. And then there will be a more comprehensive method, which essentially I like more, that somehow really gets at the heart of continuous dependence, and I'll focus on this tomorrow. Okay. So let me now discuss continuous dependence. So to do this, we have to do a little bit of somehow geometry of singular Ricci flows. Okay. And so this is a very elementary observation here, which is quite nice, I feel like. So what I did here is I drew a picture, an example of a singular Ricci flow. Okay, so it's just we start from some manifold, then we have some singular neck pinch. Maybe this part might be a sphere. Then we have another neck pinch. Then this is another sphere, and this is maybe a torus or something else with topology or whatever. Okay. And these arrows indicate the time vector fields. Time vector field. Okay. So let me define what a world line is. So a world line is just the trajectory of the time vector field. So it just corresponds to a non-moving point in a conventional Ricci flow. Okay? So this would be an example of a trajectory. And I'm going to use the following notation. So if gamma is a trajectory, and if it's parameterized in the way that somehow, the trajectory at time t is contained in the time slice of time t, then I'm going to write xt to be equal to gamma of t. Okay, so if I'm given some point x, then xt, x in parentheses t, will just be the point on the world line through x, intersected with the time t slice. Okay. And so of course there's a corresponding point x0, which is just the projection down to a 0 along the trajectory. So the time vector field is not a complete vector field. And so there are trajectories or world lines that are not defined on the entire time interval. Okay. And essentially what happens to those is that they more or less run into some singularity. And so then here's some kind of hole and they cease to exist. Okay. Recall the time vector field is always non-zero because the time vector field applied to the time function is always 1. Okay. So it's really like a completeness issue here. It's not that this exponentially converges to something. Okay? Okay. So now I'm going to call a point x in some time slice to be a bad point if we can follow the world line all the way back to time 0. So if x0 does not exist. Okay? So if the backwards world line is incomplete. Okay? So bad points are those that run into singularities if we move backwards in time. And so here's a nice observation that is due to Kleiner and Lott. They proved that there are only at most finitely many bad points in every component of every time slice. Okay? So if you take a component here, this is essentially the picture that I see. There are only finitely many ways that I can run into a singularity. Okay? So I won't prove this here, but let me just hand wave why this could be true. Okay? So the main idea of this proof is that, well, if we somehow look at points somehow slightly after where this singularity resolves, and we look at the corresponding points of these bad world lines, then we see these, these caps which look like Bryan solitons, and these caps have a lot of positive curvature at the tip. Okay, so distances will contract, and since these caps go from scale 0 to to some macroscopic scale, the curvature there will go basically to infinity if we go backwards in time. So we see some contraction to an infinite extent. So essentially, this will show that any two, this will somehow show that we have, any region here which is singular will somehow contract as much as we want to, and will only limit to a single world line. So that's somehow the idea. And you also might say, well, there may be an accumulation of singular times. So why do we only see finitely many bad points? And that the reason for this is that very often singularities are somehow behind each other. Okay, so if you wanted to somehow, if we maybe look in this time slice, then there's somehow a bad point due to this world line. But then this singularity is somehow behind the singularity. So we wouldn't be able to flow into the singularity starting from here. Okay, so this is somehow the reason why we only see finitely many bad points. Okay, so we've finitely many bad points in every component of every time slice. And so now what I'm going to do is now I'm going to consider the following set. I'll define Wt for every time t to be the projection of all the good points of the time t slice, okay? So essentially I'm just going to take all the points t here, and I'm all projecting them all down by following the flow of the time vector field. Okay? And so this is some open subset of the initial time slice, right? Of m naught or n, okay? Okay, so this is an open subset, and then I can also push forward the metric gt. So this is the metric gt that's defined here. I can push it forward via the flow of minus del t, and push it forward to become a Riemannian metric on Wt. Okay? So I'm going to call this g bar t. Okay? So now note, if I do this construction, then Wt g bar t is a Riemannian manifold, and it's isometric via the flow of the time vector field to the time slice mtgt minus the bad point, which are only finally, which are somehow discrete. Okay. All right. Are there any questions on this construction? Okay. Okay. So recall, what did we do? So we started with a singular Ricci flow, and I've described a construction for a family of open subsets of the initial time slice and metrics on these open subsets defined for all t, where, well, W2 is open in M naught. It's a decreasing family of open subsets. For if we plug in 0, we just get the initial time slice, and G bar T satisfies the Ricci flow equation. And even better, if we know WT GT bar, then this somehow obviously determines the singular Ricci flow, because all what we're missing here are these this discrete set of bad points. Okay, this will fully recover the geometry of the corresponding time slice. Okay? So one way of phrasing continuous dependence would be to say, well, why don't we talk about the continuous dependence of this object, because this is defined at time 0, and it doesn't depend on the choice of the singular Ricci flow. Okay? And so now I can state continuous dependence of singular Ricci flows in this quick and dirty method. So I'm going to fix some closed 3 manifold, and then the statement is the following. So then for any Riemannian metric, let me consider some singular Ricci flow, M upper mg, right, with this as the initial time slice. Okay? And again, this is unique up to isometry. So this will give us a uniquely defined map from G to some singular Ricci flow. Maybe this is not that unique, but then if I extract this information out of this, this is uniquely determined based on G. Okay? So this is some other partially defined Ricci flow starting from G. And now the statement of the continuous dependence theorem is that this map from here to here is continuous in the local C infinity topology. Okay? So meaning that if I vary G continuously such that all its derivatives vary continuously, then this will vary continuously as well. Okay? Okay. So now I have to be a bit more precise. What does this mean precisely? What does the continuous dependence mean here? And there are several ways of stating this. There is a topology on the space of all these kind of flows, but let me not, maybe just for time purposes, state this in terms of what sequential convergence would mean for these kind of guys. Okay, so let's assume that I have a sequence of gi's going to some g infinity in the local smooth topology. Then for any time, first of all, we have some kind of continuity of these open subsets. And the continuity will be that Wt infinity is contained in the limit of these open subsets Wit. Right? So by this, I mean that if I take a compact subset of the limiting set, then this compact subset has to be contained in the Wit for large I. Right? And we have smooth convergence or local smooth convergence of the corresponding metrics GIT and their derivatives. Okay, so note, it's important here that we don't have any better convergence. So it may happen that all the WITs are M, but then in the limit, the flow would correspond to some singularity flow, and therefore W infinity T would be not equal to M. Okay. All right, so okay, so let's see. Are there any questions so far? Okay, so I didn't expect this, but I seem to still have some time. So maybe I'll start with what I plan to do in lecture 4, and I may recap some of these things again. So I'll just give you some of the first outline in this lecture 4. Okay, so what I want to do in lecture 4 is I want to somehow talk a bit more about the topological applications of, especially of the uniqueness theorem, or more precisely the continuity of singularity flows. Okay, and remember the topological applications were the generalized Smale conjecture, where we analyzed diffeomorphism groups, and this conjecture concerning the space of positive scalar curvature metrics. And so I'll structure this lecture as follows. So first of all, I'm going to show you a short but only partial proof of the generalized Smale conjecture. Okay, and this proof, I think we published this in a paper, which is, I think, about 30 pages, and 20 pages are just some, technical preparation. So the argument is really on 10 pages. It's a very short argument, assuming that we have all the continuity results. So I hope I can present this proof almost completely. But this will only prove the generalized Smale conjecture if except in the S3 and RP3 case. It's not a complete proof. And then I want to focus on the full statement of the generalized Smale conjecture, and also on that conjecture concerning the space of positive scalar curvature metrics. And so in order to do this, we have to revisit somehow how we interpret continuity for families of singular Ricci flows. So there will be a brief analytical discussion here, and then I'm going to conclude with some sketch of how we can prove this the topological, the remaining topological conjecture. So this will be a bit more technical. I'll just give some outlines on how to do this. Okay. All right, so let me start with this short, or I would say partial proof of the generalized Smale conjecture. Okay, so here's the setup that I want to consider. So I'm going. The generalized Smale conjecture concerns spherical space forms. Right? So let M be some spherical space form. So it's S3 mod gamma, and I want gamma not to be 1 or Z2. So I want M not to be S3 and not to be RP3. So you'll see in a moment that somehow this technique breaks down in these cases. And I'm also going to assume that the Smale conjecture is true in the S3 case. So this was proven by Hatcher. Right? So this was that the diffeomorphism group is homotopy equivalent to its isometry group, which is O4. Okay, so this is the other drawback of this approach, that we can't reprove Hatcher's theorem. So we have to use this again. All right. Okay, so now what will be our goal? Well, it will be to show that the space of constant curvature metrics on M is contractible. And I showed you in the very first lecture that this is equivalent to saying that the diffeomorphism group of M is homotopy equivalent to its isometry group. Okay, so this is enough to show this. And so recall, in dimension 2, we had a proof of this statement, which used the Ricci flow. So the idea was to use the Ricci flow to construct a contraction, retraction from the space of metrics to the space of constant curvature metrics, or even a deformation retraction, okay? This space is contractible, and so this would imply that this space is contractible as well. Okay? And so this is some of the same hope that we want to, it's the same strategy that we would like to follow. Okay? So, but now we have to be a bit more careful, like the deformation retraction in dimension 2 was just given by the Ricci flow, right? We just had to do some rescaling or maybe take a limit in order to construct this map. Okay? Now, given a metric, we only get a singular Ricci flow. So essentially, we have this, I'm being a bit ambiguous here, but essentially we have this map from the space of metrics to some kind of space of singular Ricci flows, whatever this should be. And then we will need a map from the space of singular Ricci flows to the space of constant curvature metrics. We can't just take a limit of these singular Ricci flows, because singular Ricci flows don't converge to some kind of constant curvature metric on the time zero slice. I mean, we might have neck pinches, we may have different constant curvature metrics in the limit and so on, okay? So we really now have to worry about how to construct the second map. Okay, so the question will be, given some singular Ricci flow, how can we extract a constant curvature metric from the singular Ricci flow? And how can we do this in a continuous fashion so that given the initial metric, we produce some kind of continuous family of these guys? All right, any questions on this? Okay, so maybe I'll just show this slide and people can think about this while, and then today or tomorrow morning, and then I'll review this again next time. So let me just fix a singular Ricci flow, and I want to somehow vaguely discuss how can I use this singular Ricci flow to construct a constant curvature metric at the initial time. Okay. I somehow want to find some recipe of extracting this constant curvature metric. So now, in order to do this, we need to do a little more geometry of singular Ricci flows. And so here's an observation. So I said we're starting from some spherical space form, so which is not S3 or RP3. And so what happens to this singular Ricci flow? So, well, the flow will flow for a while until we hit the first singularity, let's say some neck pinch. And at this neck pinch, the flow will split the manifold into two pieces such that the original manifold is a connected sum of both pieces. Right? So after performing this step, M is going to be a connected sum of time slices in here and time slices in here. Okay? But spherical space forms are prime. That means if we represent the manifold as a connected sum of two manifolds, then one of the two summands has to be the three sphere. Okay? It has to be the trivial three sphere. Okay? So this means if we somehow undo a connected sum here, one of these two components has to be the three sphere and the other component has to be diffeomorphic to M. Okay? So let's say this is the guy that's diffeomorphic to M, and that's the guy that's the three sphere. This three sphere will just go extinct. Let's forget about this one. Then we follow the flow again until we find another neck pinch singularity. And then we again decide which one is the three sphere and which one has the topology. Okay? And so we always follow the component that is diffeomorphic to M. And at some point, when we do this, our curvature will increase further and further. And at some point, it will turn out that this entire time slice will be covered by epsilon, will satisfy the epsilon canonical neighborhood assumption. So at some point, this entire time slice will locally look like a kappa solution. And so now, given the topology of this manifold, the only way that we can be locally covered by kappa solutions is if the entire manifold is diffeomorphic to a kappa solution. Okay? But now every kappa solution every compact kappa solution that's not S3 or RP3 has to be isometric to the round sphere. Okay? So that's where somehow the restriction comes in, that M is not equal to S3 or RP3. Okay? Okay? So this shows that eventually this region will look very close to a round spherical space form, okay? Because there are no other kappa solutions of that topology. Now, if we start then eventually, so we are the geometry will be close to a round spherical space form, and then this will imply that the flow will converge to a round metric as we somehow, or sorry, I should say, this will imply that the flow will go extinct at some point here and converge modular rescaling to some round metric. Yeah, so it will just correspond to some what I should say is in this yellow part, after the time where we're very close to a round kappa solution, the flow will remain non-singular and will just become extinct at some time t2. And after modular rescaling, somehow the flow will converge to a round metric. Okay? So this is some of the main idea that we're going to be using. And so the idea will be to use this round metric, somewhat projected down to the time zero slice, as somehow the main information that the flow gives us. Okay? I'll discuss this more details tomorrow, and I'll go over this idea one more time. But maybe I'm going to stop here. Okay? Thank you for your attention.
Thank you very much, Richard. Are there any questions online?
Okay. We stop the recording, or okay?
Obviously, no question in the room. So, okay, we are looking forward to your last talk tomorrow, and thank you very much for this beautiful talk. See you.
Thanks. Yeah, see you tomorrow.
See you tomorrow.
Yeah. Bye. Have a good evening. Bye.